Okay, good evening. This is Professor David J. Delosreyes. It's March 13, 2023. The time is around 8:19 p.m. Okay. I got a new topic for tonight on my advanced mathematics long form video. The the topic is actually we are still on advanced mathematics lesson number 19. Okay, and this will be the the contents of the topic will be Laplace transform formula number 5. We are now through with formula number 1, 2, 3, 4. So for tonight, I will be deriving Laplace transform for formula number 5, that is the Laplace transform of sine of omega t. Okay, sine of omega t. And this is equal to omega over s square plus omega square. Actually, what I am deriving are actually the needed formulas for the so-called solution of circuit analysis. Okay, the concentration of the formulas that I will be deriving will be on the so-called circuit analysis. Okay, I will check my camera. Okay, let's proceed. Advanced Mathematics lesson number 19, Laplace transform formula number 5, that is the Laplace transform of sine of omega t is actually omega over s square plus omega square. Okay, let's proceed with the derivation. Using Euler's equation, a raised to plus j omega t is actually cosine of omega t plus j sine of omega t. And the other one, if the exponent is negative, that is e raised to negative j omega t is equal to cosine of omega t. This is minus, so this should be minus. So this is minus j sine of omega t. So to bring out a relation of an exponential function consisting of the value sine of omega t, if we try to inspect the two resulting exponential equation, if we try to bring out sine of omega t, we must have to eliminate this cosine over here, because this is plus and this is plus, and for it to be eliminated, we perform the operation subtraction. Because if we try to perform the operation subtraction for both the left and right, actually this cancels. Okay? So if we now try to perform the operation subtraction for the left side, it will be e raised to, this is omega, e raised to j omega t, operation is subtraction minus e raised to minus j omega t equal to, for the right hand side, if the operation is subtraction, this will now become minus, but since this is plus, they cancel out. Okay? So actually, by performing the operation subtraction, we eliminated cosine of omega t. And for the second part, if the operation is subtraction, this is minus, but this is minus, so this will now become plus. Okay? Fundamental laws of operation. A minus preceded by a minus, it will be a plus. So this is now plus. Plus j sine of omega t, plus j sine of omega t, they are similar. So the resulting sum will be 2j sine of omega t. The first one will now be 0. So this is gone. Okay? And if we try to solve for sine of omega t will be the left hand side divided by 2j. So sine of the quantity omega t is equal to 1 over 2j times the quantity e raised to plus j omega t minus e raised to minus j omega t. This is the needed relation, okay, for us to derive the Laplace transform of sine of omega t. Instead of using this, we will use this one. So if we now try to take the Laplace transform of sine of omega t, the Laplace transform of sine of omega t, this should be equal to the integral from 0 to infinity, I'm following this, 1 over 2j, that is sine, right? Times e raised to j omega t minus e raised to minus j omega t, close bracket, times this exponential function over here. That is standard for taking the Laplace transform of any function. Okay, e raised to minus st, because we are transforming this function of t here to a function of s. So there is an s over here, times e raised to minus st times differential time. If we try to expand the right hand side, 1 over 2j, 1 over 2 is a constant, and j is still considered a constant, so we bring it out. So this should be 1 over 2j, the integral from 0 to infinity. We multiply this one by this, we apply the laws of exponent, it will be same base, different exponent, so it will be e raised to j omega minus s. There's a common factor t, times close quantity times time. The second part will be, this is minus, right? So e raised to, if we multiply this one by this, it will be e raised to, it will be same, what do you call this, simplification. Same base, different exponent, so it will be same base, plus the sum of the exponent. Minus j omega minus s, minus j omega t minus st, we factor out t, so this is minus j omega minus s, close quantity times time, close bracket, times differential time. Okay, so this is now integrable, and so it is. But we was have to verify the complete differential of the two exponents. The exponent of the first one is j omega minus s times time. If we try to bring out the complete differential, du will be j omega minus s. J omega minus s is constant, right? So it will be j omega minus s times differential of t, which is differential time. Or du will be just simply j omega minus s times dt. It is not exact. So for it to be integrable, we introduce the reciprocal of this outside, and this is the reciprocal. Okay. For the second one, it's the same. U is minus j omega minus s close quantity times time. Du will be minus j omega minus s close quantity. The differential of t is just simply dt, and this is not exact. Okay. So for the second one to be integrable, under the integral of e to the u du, we introduce the reciprocal of this one, and the reciprocal is this one. Okay? So after the introduction of the two reciprocals, the integral of the two terms will just be simply e raised to minus j omega minus s times time. The second one will be the negative thing. It will be e raised to minus j omega minus s close quantity times time, close bracket, with the limit from 0 to infinity. Simplifying this one, this should be 1 over 2j, 1 over j omega minus s. Okay? For the meantime, forget this one. Just consider this one. Then apply the limit infinity and 0. As was discussed from the previous discussion or lesson number 18, this is actually 0. If we put time t to be infinity, this will become 1 over, it will become e raised to negative infinity. And if we try to simplify this one, it will be 1 over e raised to infinity. This should be 1 over a very big number. And 1 over a very big number, this is almost 0. So the first one, when we place time to be infinity, the limit will be 0. Okay? Oh, well, we are just substituting the limit. but you should know how to perform the operation involving infinities. When time t equal to 0, this exponent will become 0, so the next one will be e to 0, and e to the 0 is actually 1, so this is minus 1. Right? That is by considering the first one. Considering the second one, I will just rewrite minus 1 over minus g omega minus s. Again, you apply the upper and lower limit. For the first one, this will become 0. When time t is 0, the lower limit will be minus 1. So this is minus 1. So what will happen? This will be 1 over 2j, okay? This negative, right? I will bring down this one. So the denominator now of the first term will be this s here times minus 1 will be plus s. J omega times minus 1 will be minus j omega. I maintain the sign of the numerator to be plus 1. Okay? Minus. Okay? This minus. I still maintain the sign of this to be minus. So this is minus. Then I will try to bring this negative 1 here on the denominator. So minus 1 times s will be positive s, and minus j omega times minus 1 will be plus j omega. So actually the simplification is 1 over 2j, open bracket, 1 over s minus j omega minus 1 over s plus j omega, close bracket. And this now involves the addition of two fractions with different denominator. As what Mr. Ben said, you use the what you call this butterfly method. The simplification will be the product of this, the product of this minus the product of this, and the resulting denominator will be the product of the individual denominators. So okay, let's proceed. So 1 times s plus j omega is this one. Right? I remove the bracket already. The quantity. Minus. Okay? 1 times s minus j omega will be minus. I put the quantity. It's very critical. There's a negative sign over here. Quantity s minus j omega. And the resulting denominator is actually the product of this. The middle term will disappear. So s minus j omega, s plus j omega, okay? S times s will be s squared. The middle term will be minus j omega plus j omega. So actually the middle term cancels. And the last term will be minus j times j will be minus j squared. And omega times omega is omega squared. So this cancels. So what comes out is simply s squared minus, we replace the value j squared by minus 1 times omega squared. So what comes out will just be simply s squared plus omega squared. Meaning if we try to simplify this one, what will just come out will be simply s squared plus omega squared, and this is a simplification. Okay? And for the numerator, okay, it will be s plus j omega. Okay, let's now try to remove the quantity. Minus 1 times s will be minus s. Minus 1 times minus j omega will be plus j omega. Okay? So this s here cancel with this. So what will remain on the numerator will be j omega. They are similar terms. This is 1, so it will just be simply 2j omega. Okay? All over s squared plus omega squared times the 1 over 2j. And luckily, this 2j here cancel with this. So what comes out now for the Laplace transform of any sine of omega t, this should be equal to omega all over s squared plus omega squared. And this is formula number 5. It is this. Right? Okay, let's try to bring out the summary. Actually, we finished 5 transformation formulas already. Number 1 is actually the Laplace transform of 1 is just 1 over s. the Laplace transform of B sub O, meaning the initial voltage, B sub 0, is actually B sub 0 over S, where B sub 0 is actually a constant. Okay? So they look similar, right? The Laplace transform of B sub 0 will be B sub 0 over S. We are needing this in the so-called solution of circuit analysis after finishing all the transformation formulas. Because after deriving all the formulas that we need in the so-called circuit analysis, we are needing all this. Okay? And number 3, the Laplace transform of A raised to AT is actually 1 over S minus A. And the last topic, the last time around, the Laplace transform of cosine of omega t is actually S over S squared plus omega squared. And for tonight, the Laplace transform of sine of omega t is actually omega over S squared plus omega squared. So memorize this by heart. To solve a problem on the circuit analysis using Laplace transform, we must have to memorize this formula 1 to number 5. There are still some formulas, but for tonight, I am requiring you to memorize formula number 1 to number 5. That is Laplace transform of 1 up to Laplace transform of sine of omega t. You should memorize this one because under integral calculus, if you have memorized around 100 formulas to pass the integral calculus, I think there's no problem in memorizing some of the transformation formulas under Laplace transform. Our main topic will be circuit analysis. The other topics, that will be another topic maybe already. Okay guys, so for those who are taking up advanced mathematics, this is for you guys. Okay? If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. And if you want to share it, please click share. Good evening from Los Angeles.